So thanks everybody for coming to our last marine science seminar, the last regularly scheduled one for the semester. We will probably have some student defenses and some other things we'll advertise, but the official series will start again in the fall. And if anybody has recommendations for future speakers, feel free to email me about that. But today I'm happy to invite our guest speaker, Corinne Trott. Corinne just recently became officially a federal oceanographer at NRL, but had been here for a couple of years as a postdoc, working with Joe Metzger at NRL, but through USM. So she's been in the Saucy community and the Stennis community. Her background is in atmospheric and oceanic sciences in her bachelor's from University of Wisconsin-Madison, and then a PhD in marine science from University of South Carolina. And her focus is on physical oceanography and satellite oceanography. And she's been very busy with publications lately, so I encourage you to check those out. And I think we'll be hearing about some of her latest work today. So let's welcome Corinne.
That's right. Thank you, Chris. Thank you for that introduction. So yeah, like Chris said, this work was done while I was a postdoc for the University of Southern Mississippi while working at the U.S. Naval Research Laboratory. So I just want to start off by thanking my institutions, thanking the SOCI community. I've been following this seminar series for a while, and I'm really excited to be a part of it. So thank you for inviting me out and for taking the time out of your day to listen to my research. This research was funded by the NRL 6.1 South China Sea Dynamics Project. And a lot of the work that I'm going to be discussing today was recently accepted for publication in Ocean Dynamics. And it's been accepted, and I'm going through the proofing stages now. So if anyone has any interest in contacting me about this research a little bit more, or maybe getting a PDF of the paper, just let me know. And as soon as I get it, I'll pass it along. So I want to do a shout out to my co-authors as well, Joe Metzger and Zitao Yu, both of which are on the South China Sea project and just have been instrumental in this work. So that being said, today I'm going to be talking about my work on investigating eddy characteristics in the South China Sea and Luzon Strait. So today I'm going to discuss the objectives of this research and then introduce the region, both where is the South China Sea, where is Luzon Strait region, and talk a little bit about why the dynamics in this region are very unique with respect to eddy dynamics and eddy generation and eddy propagation. Essentially, the Luzon Strait region is a gap that has the South China Sea to its west and the Kuroshio and North Pacific Gyre to its east. So it experiences a lot of exchange between very different water masses, and it's just a very exciting region. And then our results in this paper are separated into three major categories. The first of which is using an eddy tracking technique to identify eddy characteristics, location, amplitude, radius, kinetic energy, and get a feel for the general circulation of the region and how it differs on both sides of Luzon Strait, but also in the strait itself. Next, these eddies are filtered down to just eddies that fit the definition of Kuroshio eddy shedding. And Kuroshio eddy shedding is a very unique type of eddy generation where it initiates in the water mass of the North Pacific Gyre to the east of Luzon Strait, and then it is either carried by or crosses the Kuroshio to the west of Luzon Strait, and then it sheds into the northern South China Sea. And that's really unique because sometimes depending on the basin scale circulation, it can propagate as far west as the Chinese coastal shelf. So it just influences air-sea fluxes, heat and salt transports, and it's also a non-deterministic process. So it's definitely exciting to identify. And then the last section of the results that I'm going to cover today revolves around Kuroshio pathways in the Kuroshio South China Sea Index. From this point on, if I refer to KSI, this is the index that I'm talking about, where essentially it's an index that uses surface currents to identify the state of the Kuroshio. Sometimes it crosses into Luzon Strait and then out. Sometimes it doesn't enter Luzon Strait at all, and sometimes it bifurcates into a northward branch that doesn't go into Luzon Strait and a westward branch that does. So there's been a couple different approaches to the KSI, and I'm going to discuss that more in detail today. Then I'll conclude this work and discuss what I'm doing now and what I'm doing in the future. So keep an eye out for future research. So the objectives of what I'm talking about today are to accurately quantify surface characteristics and behavior of mesoscale eddies in the Luzon Strait region over a 26-year period. This 26-year period is based on the altimetry era. At the time that this research was started, the full years of available altimetry data were from 1993 through 2018. So that's the time period of study now. The next step was to develop and modify an eddy tracking algorithm to identify Kuroshio eddy shedding events. And part of that is just the identification of the proper algorithm. And then the other part of that were finding what criteria Kuroshio eddy shedding events would meet. And then after those eddy shedding events were identified, then we provide an in-depth focus on eddies with the farthest westward propagation. And like I said, these can propagate so far that they influence upper ocean circulation offshore of the Chinese coastal shelf. So this is a general current schematic of the North Pacific Ocean with major identified currents, and the region of interest today is this boxed region to the lower left, the South China Sea. I'm not sure. Can you guys see my mouse when I move it? Okay, nice. Yeah, so it's this region, the South China Sea, which is bounded by the Kuroshio, which is the western boundary current of the North Pacific Gyre. The South China Sea is a semi-enclosed sea and the largest marginal sea that's influenced by the Kuroshio, but also is a pretty essential part of local transports in this region. It's a part of thermohaline circulation where there's highly varying transports that cross through Luzon Strait, and then ultimately the outflow point is in this maritime continent region. So it's important to be able to identify what type of momentum fluxes and eddies shed into this particular region, and then see how the currents change and how the upper level dynamics change. So to the right here, I have just general bathymetry of the region, and you can see, again, like I said before, as far as marginal seas go, the South China Sea is relatively big, it's relatively deep, and to the left, I'm going to show an animation of absolute dynamic topography. So in this work, I selected absolute dynamic topography over sea level anomalies for a very specific reason. And that reason is, if you look at the absolute dynamic topography, the North Pacific Gyre is an extremely clear and strong and somewhat variable. You can see the eddies that propagate westward along westward propagating Rossby waves in the North Pacific Gyre, but the most important thing that you can gain from absolute dynamic topography is just the difference of dynamic topography east of Luzon Strait, which again is right here. This is the region in question. You can see high ADTs east of Luzon Strait and much lower ADTs west of Luzon Strait. And this interbasin pressure gradient is primarily what drives the Kuroshio. It's, like I said, a western boundary current of the North Pacific Gyre. So if you look at where the biggest ADT gradient is, that typically follows the same pathway of the Kuroshio. And you can see in the ADT how the Kuroshio is relatively tight downstream of Luzon Strait region, but within Luzon Strait, it's highly variable. And if you're lucky, when you look at the animation, oh, there was a good one. You can see some of these Kuroshio eddy shedding events where It's clearly waters that initiate with the North Pacific Gyre and then propagates westward into the South China Sea. And here are geostrophic currents that essentially reflect the same currents that we would have expected to see in the absolute dynamic topography on the previous slide. So if you look at, again, upstream of, or my apologies, downstream of the Kuroshio, it's a very tight, very strong current, but in the Luzon Strait region, it responds to eddies. Oh, there was a good looping event. Sometimes it intrudes into Luzon Strait, sometimes it leaps past it, and it's a very unique and interesting current in this region. So here is a generally accurate but definitely oversimplified schematic showing the dynamical factors that contribute to Kuroshio intrusion. The South China Sea falls under upper level currents that respond to the monsoon regime. And while it's not as responsive as, say, the Bay of Bengal, where immediately currents completely reverse twice a year as a response to monsoon winds, it still is impacted by less strong but still highly seasonally varying monsoon winds. So that gives the currents some sort of seasonality, as do eddy characteristics. So in this general schematic, you can see how winds can intensify that interbasin pressure gradient from the absolute dynamic topography. It can create wind-generated mesoscale eddies, and ultimately shape the upper level of the ocean to facilitate Kuroshio intrusion. And Kuroshio intrusion and eddy shedding events from it affect the local heat and salt budgets, eddy generation, and circulation in this region. So on the left, I have a schematic which just shows potential pathways of the Kuroshio across Luzon Strait. And you can see that coming into Luzon Strait, of course here it's just a schematic, but real life currents tend to reflect it. They roughly take the same pathway in. And that is typically determined by the local bathymetry, by the local island chains. Joe Metzger has done some really great work modeling how essential it is to accurately represent these island chains, because if they're not well represented, then this inflow angle of the Kuroshio into Luzon Strait region is going to be inaccurate, and then everything after that is going to also be inaccurate. So it's really essential that the bathymetry is correct, that this angle of the current coming into Luzon Strait is correct, and that there is a notable influence of these local islands. But what this schematic shows is just how varied these pathways can be. Some of them barely go into Luzon Strait and then continue on, and sometimes it loops. And it was initially suggested that when the Kuroshio intrudes into Luzon Strait and loops and pinches off, then it would create an anticyclonic eddy, and then that anticyclonic eddy would, depending on the local currents, the basin scale currents, propagate in whichever direction it's advected, which is possible, but it's also possible that it bifurcates into this westward branch where the Kuroshio is still going into and across Luzon Strait, but it doesn't necessarily loop back to create a full eddy and ends up just creating a South China Sea branch of the Kuroshio current that goes westward instead of in that loop and then northward out of Luzon Strait again. And then to the right, I have some seasonal averages, just some seasonal climatologies in the wintertime and summertime. And the top row is at 15 meters depth, and then the bottom row is using AVISO. So AVISO refers to the altimetry data, so it's satellite surface level, and you can see that not only is there a strong surface current of the Kuroshio, but there's also that subsurface component as well. So it's a very strong current. It's very important for understanding eddy shedding. So here I'm about to play an animation, and this is just one single isolated event of an eddy that sheds from the North Pacific Gyre across the Kuroshio and then into the northern South China Sea. So that's really the crux of what we're trying to isolate here and see, is this something that we can not only identify, but something that then we can apply criteria to and then identify in perhaps big data sets without going map by map, frame by frame, and identifying these. So you can see that it clearly crosses the Kuroshio and then completely independently pinches off. And I'll play it a few times, but yeah, you can see that it clearly, when it starts, it's in that North Pacific Gyre water, and then by the time that it ends, it's completely crossed the domain with complete westward propagation that goes all the way to that Chinese coastal shelf. So it's really important because that then is going to influence upper level circulation in this region. So like I said before, this work has been accepted for publication in Ocean Dynamics. So the title of that paper is Investigating Mesoscale Eddy Characteristics in the Luzon Strait region using Altimetry. And again, feel free to email me or contact me if you'd like to have this paper or just want to discuss this a little bit more. And this is another opportunity for me to thank my co-authors, Joe Metzger and Zitao Yu. So the data that I used in this work, like I said, I used the CMEMS or Aviso Absolute Dynamic Topography. This is an altimetry product, and the reason I put CMEMS and Aviso is because it's something that's been very commonly used, and it used to be hosted by the Aviso website, and now it's the same data, it's just through CMEMS now. And I use daily data with quarter-degree grid spacing, and I use the absolute dynamic topography over sea level anomaly because while sea level anomaly, it's very good for eddy studies because it gets the local minima, local maxima, and I mean, eddies themselves are anomalous altimetry features, but in this particular case, we're trying to identify eddies that start in one water mass and then go to another water mass in the Kuroshio eddy shedding, where if you use sea level anomalies, it's not likely to retain the North Pacific Gyre. So because I need to be able to clearly see, did this eddy start in the North Pacific Gyre, cross the Kuroshio, and then leave the North Pacific Gyre and enter the Northern South China Sea, it's important to use ADT instead of SLA. So generally in eddy tracking studies, sometimes they use ADT, sometimes they use SLA, and it really depends on your region and what type of features you want to retain and what type of features you don't necessarily need. Because I've done some work on eddy tracking in the Arabian Sea region, and in the Arabian Sea, there's no large North Pacific Gyre to deal with. So it depends what type of feature you want to retain, what type of features you don't, but either one is going to have these local minima maxima. So again, also depending on which eddy tracking approach you use, the one that I use, you just need the local minima and maxima. So ADT and SLA should both be able to identify the same eddies. And then to get composites of temperature, SSS, and SST signals of the eddies, I used SMOS and AVHRR. SMOS is the earliest launched sea surface salinity satellite. It was launched in 2009 and still active. There have been two since then, Aquarius and SMAP, but because SMOS spanned the longest time frame, it was the earliest launched and it's still active. That was the one that I selected for this particular work. And then the AVHRR is the optimally interpolated SST product from NOAA and CDC. And then the bathymetry used in this work is from GEBCO, which is the general bathymetric chart of the oceans. It's got 1/240th grid spacing and involves it integrates quite a variety of observations, including satellite-derived gravity data, single beam and multi-beam echo sounders, seismic methods, LiDAR, and electronic navigation chart soundings. So the eddy tracking algorithm that I used here, and I've used it in a couple other regions, namely the Gulf of Mexico, Arabian Sea, and Bay of Bengal. But basically the way that it works is as long as you have a sea level anomaly map or absolute dynamic topography map, first it finds the local minima and maxima, where in this situation, minima correspond to centers of cyclonic eddies, maxima with centers of anticyclonic eddies. And then it finds these centers and then it grows outward until it finds the outermost closed sea level anomaly or ADT contour. So then once you have that on each map, that identifies the center and then the eddy edge of each individual eddy. So that is done for each daily map from 1993 through 2018 for the Luzon Strait region. And then in order to create trajectories, this schematic shows the approach that the algorithm takes in order to identify each individual step of eddy propagation. Where if this panel A is the contour at time t, and then the dashed line is the contour at time t plus dt, which in this case is 1 day, but depending on your data set, you might have different time steps. I would advise using higher frequency time steps rather than weekly data for eddy tracking, but daily is fine for the mesoscale. So these dashed lines indicate potential d plus dt contours. So in the case of panel E, panel D, and panel F, there's only one additional contour, and it's pretty clear to the algorithm where the next step in the track is. So then it continues to the next step, and then looks at the next day's eddy map, and then tracks it from generation to dissipation. If it's like panel B, where there's no intersecting eddy edge between time t and time t plus dt, the algorithm stops. And if you have something like panel C, where the eddy actually splits, then it minimizes this cost function here, which uses statistics of radius, amplitude, and EKE to continue the trajectory with the most statistically similar eddy. And then the other one is a completely new track. So that's how it identifies the eddies and then tracks them throughout their full lifespan. So here is monthly absolute dynamic topography. You guys saw the animation a couple slides ago, but there's a lot of variation due to high amounts of eddying, just high amounts of variability. So here is just the climatology, and you can see pretty clearly how strong the ADT interbasin pressure gradient is between east of Luzon Strait and west of Luzon Strait, which leads to a stronger corrotio. But when you look at the monthly ADT, you can see very strong or very low absolute dynamic topography in the northern South China Sea during the wintertime months, and very high dynamic topography in the North Pacific Gyre in summertime. And again, this region responds to monsoonal winds, monsoonal variability, so that's one of the things that really drives this variability. So how does this affect the eddy field? So here is standard deviation of the monthly climatology of ADT from the previous figure. And not always, but typically regions of high standard deviations correspond with regions of high eddying and high eddy variability, which we prove later in the paper is true here. And what we see is, in accordance with these unusually high absolute dynamic topographies in June, July, August, September, east of Luzon Strait, there's also high variability of that absolute dynamic topography. So you saw in the animation that corresponds to pretty substantially large eddies, but what is most interesting for the sake of Kuroshio eddy shedding in this figure is if you look at January, and the black line is the 1,000-meter isobath, there's this quasi-circular feature that happens to be right at the point of Kuroshio eddy shedding and what's called the looping path of the Kuroshio into and around the Luzon Strait region. So that was kind of unique because it's a feature that we know about but didn't necessarily know the seasonality of. So that was a new finding. So these figures show spatial eddy characteristics, and basically what this does is every eddy identified from 1993 through 2018, its radius, amplitude, and EKE are identified, and then it's spatially binned into, I believe here I have 1/4 degree pixels. So this really shows, like in the top row, where are the most eddies? And in the second row, where are the highest radii, highest amplitude, highest EKE, et cetera, et cetera, et cetera. So we can confirm what we saw here, where there are very high radius, high amplitude, high EKE eddies east of Luzon Strait associated with the North Pacific Gyre. But there's also an unusually high number of specifically anticyclonic eddies in that eddy shedding region, which is exciting and again validates this Kuroshio eddy shedding phenomena. So it's really exciting that we can see that in specifically identified anticyclonic eddies. So like I said before, the currents of the northern South China Sea respond to monsoonal winds, the monsoonal regime. So it's not a complete basin-wide current reversal like you see in the Bay of Bengal. Some currents are the same, some of them respond seasonally. So you can see in the left panel and the right panel, the Kuroshio is roughly the same. The South China Sea branch of the Kuroshio is roughly the same. But then you have other currents like these coastal currents, namely the Guangdong coastal current and the South China Sea warm current that show variability, as does the South Vietnam offshore current. So this figure here shows seasonal eddy characteristics, and it's essentially the same thing as the spatial map shown here, except now it's seasonally averaged and separated between east of Luzon Strait and west of Luzon Strait. And it really reinforces the seasonality of these eddy characteristics that we see. And basically, amplitudes and geostrophic velocities of eddies east of Luzon Strait are significantly greater, significantly more energetic. But west of Luzon Strait, there's that one isolated region of high numbers of anticyclonic eddy generation, which corresponds with that Kuroshio eddy shedding region. So this figure is from Zhang et al. 2018, and I'm going to discuss more about panel B because it has a lot of information. Panel A essentially reinforces that the region that we're looking at experiences high eddying. But panel B in the color shows sea surface temperatures, in the white line shows bathymetry, and in the black line shows sea surface salinity. And in the red, it roughly shows the Kuroshio across Luzon Strait. And this is really interesting because the sea surface temperatures roughly show a gradient that's oriented at about 45 degrees west of Luzon Strait and negative 45 degrees east of Luzon Strait. But if you look at the salinity contours in black, it's very clear that the waters of the western North Pacific have significantly higher salinities than they do in the South China Sea and west of Luzon Strait. So this is significant because if you're talking about eddies that propagate from one water mass across the Kuroshio to the other water mass, well, how does that influence temperature and salinity? And with salinity, it's clearly significant because it's going from approximately 34.4 PSU to 33.8 PSU waters, which these are climatologies, so that the numbers will vary, but it's pretty significant when you look at the influence on local surface water characteristics. So here are composite surface characteristics of all the eddies that were identified from 1993 through 2018. The right side of the figure is east of Luzon Strait, the left side of the figure is west of Luzon Strait, and it's separated into anticyclonic and cyclonic eddies. And in terms of temperature and salinity, not only gradients, but orientation of those gradients, it's pretty reflective that for temperature, these background gradients of the 45-degree orientation, negative 45-degree orientation, really dominate the composite thermal structure. And we see that reflected in salinity as well. But what's really interesting here is if you look at the composites of just the physical characteristics itself, the ADT and then the speed from geostrophic currents of that ADT. If you look west of Luzon Strait, there's not a whole lot of difference in magnitude or symmetry between anticyclonic and cyclonic eddies. And cyclonic eddies east of Luzon Strait are pretty much the same situation. The only real difference is anticyclonic eddies east of Luzon Strait. And here it says 121 east. That's approximately the longitude of Luzon Strait. And you can see while the others, quadrants 1, 3, and 4, are very rotationally symmetrical, the anticyclonic eddies east of Luzon Strait are significantly stronger in flow on their westward side. And that is due to typically interactions between the Kuroshio and the eddies itself. And it's really interesting because it brings into question how important these eddies are for local temperature and salinity advections. So this schematic is also from Zhang et al. 2018, and the shaded color is surface horizontal thermal advection. And then the words cold and warm, west of Luzon Strait, east of Luzon Strait, and then that thick black line that shows the angle of that gradient, just how it's oriented, really puts into perspective how important it is that these gradients are oriented in this particular way, that when they come into contact with these anticyclonic and cyclonic eddies, the thermal advection completely changes. So this is just a schematic showing what type of thermal advection there is and where we would specifically see it, which varies substantially based on region and based on eddy circulation type. So the next step, now that we've looked at all these characteristics of all the eddies that we've looked at from 1993 through 2018, how they influence surface temperatures and salinity and where their characteristics are to really figure out which of these eddies that we've identified are Kuroshio eddy shedding events. So what we did was we applied some criteria to all the eddies that we identified. And these criteria are westward propagation, because you want it to propagate from waters east of the Kuroshio to the west of Kuroshio, generation within this box that's on each panel. And I played around with the box a little bit, expanding it to the west, east, north, south, and this one just happened to be the most accurate that I could find. A minimum amplitude of 5 centimeters and at least a 7-day lifespan, and the ADT of the eddy centroid being greater than or equal to 100 centimeters at time of generation. And again, like the box latitude and longitudes, this 100 centimeters, I tried a couple different numbers and 100 centimeters tended to be the most accurate. But the reason for this ADT criteria being applied at all is, again, just to make sure that it's going from these higher ADT North Pacific gyre waters to these lower ADT South China Sea waters. And if you look from year to year, the ones in black are the successfully identified Kuroshio shedding events. The cyan are, which you can really only see in 2000, are eddy shedding events that weren't captured by the criteria, and red are eddy shedding events that were missed. So why? So while looking at this, if you look at the year-by-year breakdown, these criteria, I would say, were successful in most years in identifying an event that had never been algorithmically identified before. So that does bring into question, well, what about those missed events or misidentified events? Well, what happened? Was there something wrong with the criteria? Was there an issue? So here are the 5 Kuroshio shedding events that were missed. And there's a little bit of variation between the reasons that they were missed. This one in 2000, you can clearly see generates south of the box. Other ones were just low amplitude, low ADT. And as for the misidentified events, most of them that were misidentified, they met the criteria, but they generated west of the Kuroshio, which indicates that if I were to do this again, perhaps I would use stricter criteria, but it's always a balancing game when you're working with so many sporadic and transient events, where if I apply more strict criteria, then this number will go down, but this number will go up. So overall, between balancing the two, I'd say the algorithm and the criteria did quite well. So this is the characteristic distribution of eddies that propagated across Luzon Strait. And we find that, so this upper left is minimum longitude, which is really westward propagation. So how far did this eddy propagate once it crossed Luzon Strait? And then the rest are typical eddy characteristics like amplitude, radius, or EKE. And we see that over half the eddies that generate in Luzon Strait dissipated before propagating across 117.5. And then the next component of our analysis was based on the eddies with the 10 eddies with the highest westward propagation, which initially was a somewhat arbitrary number. 10 eddies is, it's a pretty clean number, but when we look at the westward propagation, those 10 eddies are this block right here, which are the only eddies that crossed 113 east. So even though it was initially an arbitrary number, it ended up being absolutely correct because it does reflect the eddies that propagated the farthest west. And this is just another comparison of the eddy characteristics between amplitude, EKE, radius, and lifespan. And I was surprised by this because the red dots on these scatter plots are those 10 eddies with the highest westward propagation. And while they show to be relatively robust in terms of characteristics, they have long lifespans, which isn't surprising because they need more time to get across Luzon Strait. But I expected them to be essentially a league of their own with respect to eddy characteristics. So the fact that they're relatively, especially when you look at amplitude and EKE, that they're not necessarily outliers, I thought that was interesting for sure. So this shows the propagation of those 10 eddy shedding events. And basically this is all ADT on individual days. For the first and third columns, it's generation day. For the second and fourth columns, it's the day of maximum eddy amplitude. And just to look at it from an overview and just general trends of the behavior of these eddies, you can see a lot of them happen during the winter time and have paths that follow this Chinese continental shelf. The path is in black and the bathymetry is in gray. So you can see for the most part, there's a seasonality to these events and the trajectory follows this continental shelf. The only exception is this May through October 2013 event, where it doesn't follow that pathway, but it also happens at a certain time of year where we might not have expected it to cross that pathway anyway. This is normalized properties of those events, where basically, if you look at the x-axis normalized time, basically 0 is day of generation, 1 is day of dissipation. So this was plotted to see if there was a particular growth cycle or growth trend with these eddies. Do they peak halfway through their lifespan and then fall off, or do they peak at a certain time, or just to understand how these 10 eddies or any eddy shedding event from the Kuroshio that makes it all the way to the Chinese continental shelf, to see if there's some type of familiar behavior. And some eddies reacted similarly to one another, but for the most part, I would say it's really all over the place. Like the last one had its highest amplitude 10% into its lifespan, while this one here had it about 70% into its lifespan. So even though we've identified these events, there's still a lot of variation in the properties of them as a function of their lifespan. So the last part of my results discussion is about the Kuroshio South China Sea Index. And these pathways on the right are climatologically the 3 most common pathways for the Kuroshio, and they're referred to as looping because it goes across Luzon Strait, loops, and then comes out. The leaping path, which completely leaps Luzon Strait and doesn't really go into the South China Sea at all. And then the leaking path, which goes northward and westward and completely bifurcates. And what the KSI does is it takes a box integrated vorticity to identify this pathway. And there are typically 2 historical approaches. On the left is Nan et al. 2011, and on the right is Huang et al. 2016. And Nan et al. Had the first KSI. Basically, it looks at this box 1 region, and then it integrates all of the vorticity in that region. And this Huang index, it's really 2 indices. It's a dual index because, well, one, it uses this smaller box, but it also integrates all the positive values, and then it integrates all the negative values, and then you plot both. So the reason for this, and I think it was a good reason. One of the issues with the KSI is, say you have a looping path with really strong negative vorticity, but say on the outside of that looping path or around an anticyclonic eddy, you also have strong cyclonic movement. Then even though you have a looping path, these 2 signals could wash each other out. And that was the point of the dual index, is if you integrate them separately, you don't have to worry about that because you can see exactly what's happening. So for our region, we looked at the KSI, and it might be difficult to see, but these red asterisks are Kuroshio eddy shedding events. So we can basically say what proportion of eddy shedding events happened in each individual pathway. So this is the KSI, and this is the dual KSI, that Huang 2016 index. And in the Huang index, I just want to alert your attention to 3 significant looping events. 1 in 2017, 1 in 2012, and 1 in December 1996. And again, it seems that looping is most common in the wintertime months, and you can see that pattern throughout the whole time period. But if you look at and I just went back to the KSI index. If you look for these events, 2012 and 2017, they're still technically looping at lower magnitude. But this 1997, December 1996 event is completely gone. And I thought that was really strange because these indices both essentially rely on box integrated vorticity. So how are they coming up with such different results? And when you look at the ADT and relative vorticity on that particular day, it's pretty clear that the concerns that Huang had with the NAN method were exactly for this type of scenario, where if you look at the ADT, there's a very clear looping path. It breaks off into an eddy, but when you look at the box region, there's negative vorticity, but it's surrounded by positive vorticity. So when you separate it into these two indices, it takes care of that issue. So I am just going to conclude briefly about what I discussed today. Essentially, we looked into circulation in the northern South China Sea and Luzon Strait region and used 26 years of daily altimetry data and eddy tracking algorithm to identify and follow the trajectories of these eddies. Then we looked at the Kuroshio eddy shedding events and how their properties vary, and then took it one step forward to look at the 10 farthest propagating eddies as those most strongly influence circulation off the Chinese coastal shelf. And then we looked at the KSI in relation to Kuroshio shedding events, and we found a disproportionately high amount of shedding events during looping and leaking states of the Kuroshio. So with that, I'd like to thank everyone for attending, for taking time out of your day to listen to me discuss my research. And I'd like to acknowledge my co-authors, Joe Metzger and Zitao Yu, my organizations, USM and NRL, and the 6.1 South China Sea Dynamics Project. So before I open it up for questions, I want to talk a little bit about what I'm doing now and what I'm doing next on this research, which is basically this data set, or this research today was just focused on one data set, seeing it in altimetry over a almost 3-decade time span. So what I'm looking at right now is how these eddies vary in different HICOM environments, how they compare in forecast environments and reanalyses. I'm looking at the relationship between Kuroshio pathways, so these KSIs and local transports, as well as looking a little bit at KSIs with various different shapes and boxes, and just seeing if we can, like how Huang improved on NAN, if there's a way that we can improve on Huang. So that being said, thank you all for your time, and I'll take any questions.
Thanks so much, Corinne. I'll just help field the questions. Martin, are you ready to go?
Yeah, I'm ready. All right. Am I audible? Nice, very nice presentation, Corinne. I mean, obviously, I'm an internal tides guy, and I studied the internal tides in the South China Sea, and they're pretty strong, right?
Yeah.
And so there have been several studies where actually you see that these shedded eddies, they actually refract the internal tides as they propagate into the towards the west into the South China Sea. But do you think, could there be an opposite effect, that actually the internal tides affect the eddies or the eddy shedding? I mean, I know that there's quite a strong tidal mixing in the strait due to a lee wave breaking. Have you any, is there any indication that that may affect that eddy shedding process?
Okay, that's a really interesting question, and it's one that I hadn't thought of, because a big source of the instability that drives this eddy shedding is that ADT differential between the North Pacific Gyre and the South China Sea region, which can be enhanced by local monsoonal winds. But I wouldn't be surprised if there was also that feedback between eddy shedding and tides. I don't know if the tides would amplify that instability, or I don't know. I'll have to think about that, because that's a really interesting question. And I didn't think of it just because the winds are so strong and that interbasin pressure gradient is so strong. But like you said, internal tides in this region also very strong, and I haven't seen it in the literature, but it definitely could be a mechanism for eddy generation and Kuroshio shedding.
Yeah. The energy flux from internal tides there is about 50 kilowatts.
Oh my
Peter.
gosh.
So, yeah. I have never actually calculated the energy flux in eddies, but I would be interested to see what the difference is in the energy flux.
Yeah.
But anyway, and the other thing is that, so do these eddies that then are shedded in the South China Sea basin, do they actually alter the stratification in the long term? So is the climatology really impacted by the eddy shedding?
Yeah. It looks like at that individual point of shedding, and this is, yeah, I'm just going back to this slide showing the eddy shedding events. In the climatology, it's, so I'd say if it were influential, it would only be in this shedding region particularly, because that shows up very strongly in the absolute dynamic topography variability and in the number of identified eddies. So I believe that it does in the winter time, because a lot of the eddy shedding events happen to be from December through February. So I don't imagine it would climatologically affect the surface stratification, say outside of this box, but within the western quadrant of this box, I think it absolutely would, just because that's where that highest variability is, where we found those eddy generations to be, and for them to be really winter heavy. So I would say yes, but only in that region, and I would say most strongly in January, but perhaps throughout the entire December through February time period.
All right, thanks.
Thank you.
Xiaodong, did you have a question?
Oh, yes. Corinne, you said that there are 3 events of the crucial current, looping, what the other, leaping and breaking, intruding, right? Leaking.
Right.
Which of the 3 create eddy, or they all contribute to eddy creation?
So originally it was thought that only looping can create the eddy, because you'd see, and that's this top panel, so it loops and then pinches off, and then you have an eddy created. But what we found in this paper is, yeah, you find it in looping, but you also can find it in the leaking scenario, where if you have an eddy that, say, is generated in this region, it can be advected by that westward branch. So that was definitely an interesting finding of this work, because originally it was thought looping only, but in this work, based on the eddies that we identified, and we're able to then use the criteria and identify them as shedding events, the leaking is definitely also, it's a viable mechanism, but there could definitely be more work done to have a more dynamical background as to why that's a viable mechanism.
So leaping will not create eddy.
I haven't seen any, no.
Okay.
So.
But when the eddy is created, it will be warm water eddy, right? It can't be cold water.
Yeah, I would suspect so.
But I know you also showed cold water eddy. I missed that. How do the cold water eddy created?
So it's not, so here are the background temperature gradients, and it's west of Luzon Strait, they have this 45-degree slope, and then east of Luzon Strait, they have this negative 45-degree slope. So it's kind of unique from other regions where you'd expect a relatively homogeneous temperature, and then the eddy is either anomalously warm or anomalously cold. And when we look at the composites, there's a lot more deformation of those background gradients. Like the core in anticyclonic eddies tends to be warmer, which is not unsurprising. And then the core of cyclonic eddies tends to be cooler, also not surprising. But it's really these background gradients, and then here shows the advection of those background gradients. So it's really a combination of the eddy itself and how the eddy interacts with the environmental SSDs.
Okay, thanks.
Thank you.
So I had a question. I guess there's some parallels to be made with the loop current eddies in the Gulf of Mexico. Just wondered if you've made any general comparisons of like the frequency of eddies or the size of the eddies in those two regions, and if there's some generalizations that could be made.
Mm-hmm. Yeah. I mean, there could be, but like I'd say the biggest thing of all those is size, just because even though when you look at Luzon Strait, if you look at the x-axis and y-axis, it's a much smaller region than the Gulf of Mexico, and the eddies themselves are just such a smaller scale. And here, so I didn't discuss this, but this is a good time to. So this grayed out, so the dark gray is the land, and then the light gray is the continental shelf. And the reason that the pixels of data are taken away from the continental shelf is actually twofold. One of them is because eddies that generate in this particular region are usually really small, even for Luzon Strait standards, and they're usually just transient, wind-driven, maybe 1 or 2 day long eddies. So they're definitely not going to be Kuroshio eddy shedding events. So they're not even close. And then the other reason is I had a reviewer that was really worried about satellite data by the coast, but we're taking those pixels away anyway. But even when, basically what I'm trying to get to is size was a huge driver in trying to accurately identify these eddies. And I think there are parallels because there are probably similar instabilities. And when I talked about using ADT over SLA, the loop current is a significant region for that, because you need to know which waters are part of the loop current and which ones aren't, which one's an eddy and which one's just meanders of the loop current. So there are definitely parallels, but it's difficult because the size scales are so different.
Okay, so yeah, much smaller eddies going in there.
Mm-hmm. Yeah, for sure.
All right, any other questions?
Yeah, I had one final question. Is that what is the fate of these eddies? Like, do they just disperse through diffusion or with the surrounding waters, eddy diffusion, or is it, do they die because of they interact with the shelf topography?
I think it's a little bit of both. I think that just the highest amount of instability is at that Kuroshio eddy shedding point. So once they're generated and propagate away, then they really quickly lose all their energy and instabilities that they originally got from the Kuroshio. So part of it is they interact with the coastal shelf. Basically, any deep eddy that crosses over the continental shelf dies immediately, but for the most part, it's really fueled by all the energy that it had at generation location, and then that steadily falls off as it gets farther away from that Luzon Strait Kuroshio region.
Okay.
Hi, Chris. I had a quick question.
Oh, sure, go ahead.
Yeah, this is Ebenezer. Hi, Corinne. Yeah, nice
Oh, hi.
presentation. So
Thank
in
you.
your earlier slides, I think there was a video you showed in the northwest end where you had a very strong front that formed. And I mean, this is based off the also the image that you just showed that you took data away from the coast. I was just curious whether these eddies had any impact in the forming of those front structures in the northwest. Thanks.
Mm-hmm. Okay, so if I get the, please let me know if I have the question right, but it's about the influence of those small scale eddies that would be on the continental shelf, those usually locally wind generated eddies that just last for a couple days. How do they influence the frontal makeup of the region? And I am not sure. I imagine it would be less than these larger eddies that operate in deeper waters, operate away from the shelf. Basically, these small scale eddies that would happen coastally, they would have much less of an influence, but we also didn't want to have any kind of artifacts from coastally biased altimetry data, where I mean, coastal biases are constantly improving and constantly getting better, but I think a model study might be more appropriate to really identify how much do coastal shelf eddies influence the vertical structure and how much do Kuroshio shed eddies influence the vertical structure. And I imagine it would be higher from these Kuroshio shed eddies than these really small scale transient ones. But again, I think a model study would probably be better to answer that question.
All right, thanks.
Thank you.
All right, so I think we will close with that so we can all thank Corinne for the nice talk and hope everybody has a good summer.
Thank you.
Thank you, guys.